In this section, I'm going to focus on manipulating the size of the block and manipulating its output. So we saw that with these operations here that we get these groups where the values from 0 to 1 all get the value of 0, the values from 1 to 2 all get the value of 1, etc. And let's say that I want to increase the size of this group. Let's say that I wanted to go instead from 0 to 1, I wanted to go from 0 to 2. Well, to do that, I have to change the context of the values that I'm feeding to the floor function. So I'm going to have, let's say that I change the context of the values, and I have the values that go up to 2 also get floored to 0. So to do this, I'm going to have to do an inverse operation. So I'm going to put a divide in here, scalar divide. And let's see, I'm going to call a scalar constant node. And I'm going to put this here, and so I'm dividing by 1 at the moment. So basically I get the same thing that I did before without dividing. But as I change this, you see that now the step size also changes. Let me select this one here. So when I put this to 2, now my step size is 2. When I divide by 3, my step size is 3, etc. So or if I put like the other way around, 0.5, my step size is 0.5. The output value is still the same. So this group 1 still has the index 0, index 1, index 2, index 3. So these are still used as indices. And what I'm doing here in a way, it's choosing let's say the height of an apartment in an apartment building. So let's say that I have here the ground 0, and I have an apartment building. Do something bigger, okay, like so. And so let's say that I have an apartment building, and I define that the height of one floor is 2.5, and then I'm given the height of 9 meters, and I want to find out in which apartment are these 9 meters. Well, to do that, I can perform what I did here, which is called integer division. Integer division doesn't mean I divide by an integer. It means that I convert the result into an integer. So in this case, let's say that I divide 9 by the step size, which in this case, it's 2.5 meters. So this gives me 3.6. And now I'm going to floor this, and which means I'm going to discard the fractional part. So I'm going to get left with an integer. So now I know that these 9 meters are at the floor with the index 3. So if I would, let's say, draw the floors in here, I would know that the 9 meters would be around here. If let me put the floor number. So this is going to be floor with index 0, index 1, 2, 3. And here are my 9 meters. Now, this integer division allows me to get the indices, but what about the floor height? I want to know what's the height of this floor. Well, to do that, I just have to do a multiple and use these integers like I've shown before to make a multiple of the floor height. So if I multiply this by 2.5, what I'm going to get is 7.5. So now I know that this floor where these 9 meters are is at the floor that it has the height here of 7.5. And the other ones, no, this one has 0, this one has 2.5, this one has 5. The next one is going to have 10, etc. So what I'm doing here with this division and with this multiplication is that I'm changing the context of the value, and it's a bit of conjugation. If you remember again what conjugation was, so I have a main operation, and before and after it I do another operation that allows me to change the context and put it back. So this main operation here is the flooring operation. These two operations, in this case, it's going to be divide and the multiply. And I can put the multiply part in here to see, so I can see the multiples. But first, I just want to see that I can still, using this integer division, I can still select the group. So here I'm selecting, group 0, 1, 2, 3, etc. Even though I change their size. So let's say that I put this really small, I can still, select these the groups accordingly with, in this case, it's logic node. So let me then put the multiply part. So I'm going to put here multiply, scalar multiply, and I'm going to use the same value for it. So I'm going to have a multiple of my step size, and now I get this. So when I scroll the value here, you can see what happens. It seems like I'm choosing the resolution of this. So let's see, if I put this really big, the steps, or if I put really small, it seems like the line, it is continuous, like I connect this here directly without going through the floor operation. And as I increase the size of this, we start to see some blocks. And this can be applied also, let's say, to a texture. So I have, let's say I have this here, and this texture looks like this, right? But if I pass it through this conjugation of the floor operation, I'm going to get the same thing, but with some blocky look, and I can play with the resolution of it. So it's nice. Another thing that this is useful for is to choose the order of magnitude of a value. So let's say I have this value here, 192.837, and I want to choose how many decimal places I take off, or if, for example, if I just want the value that is in the hundreds, what can I do to do that? Well, I can apply this piece here. Let's say that I choose this and I put it down here. And as for a step size, I'm going to use a power of 10. So I'm going to choose Akita Sasagi power node because it allows me to put the value that I want in the base. So in this case, I want it to be 10. And the power value, I'm going to choose it with an integer node. So in this case, I'm going to put this here. This is at, let's say, put it at 0 and connect here. And so this is my step size. It's a power of 10. So if I turn on the input SPI, I can see that now this performs just like a regular flooring operation. So it takes out the fractional part. But if I change this number here, let's say I'm going to change this to 1. Now I don't have the 1, so it's 190 instead of 192. If I put 2, it's just 100. And of course, if I put 3, since I don't have nothing in the order of the thousands, it's just going to output 0. But if I go into negative, like I can choose how many decimal places I want to have. So in this case here, I have 2 decimal places, and here, I have 3, or if I just want 1 decimal place. So now I just have the 0.8 in there. So this is one application for this setup. Now let's look into some things that are a bit more strange maybe. I'm going to disconnect this here and I'm going to select this object called sphere decimated normals. And I'm going to turn on VPR and focus on it and check its surface. So in the nodes of this surface, I have this turbulence texture. And let's say that I'm going to replace the spot. So we have here the spot info, and I'm decimating the spot info just like I did with the scalars, but this time is with vectors. So I have the divide, the floor, and the multiply again, and I'm using the same value for the divide and the multiply. So when I plug this in here, this replace spot node from DP kit, I think, or DP filter, you can see that since I have a really small step size, it's going to look the same as if I plug the texture directly. But as I increase the size of that, you can start to see some blocks. So let's say 0.1, and you can definitely start to see some blockiness going on. So this is a way to decimate textures as well. It's an effect that you can apply here directly in the 3D without having to make a video about it. Let's see the same thing, but instead of using instead of decimating the object spot, I'm going to decimate the normals of the object. So I have here this reflections with a map applied, and it looks like a smooth ball. But if I decimate the normals, just like I decimated the object spot here with this block with divide, floor, and multiply, in this case I just had to convert the normal into a rotation and then the rotation into a normal, but we'll talk about matrices later. But if I increase the size of the step, now you start to see blocky reflections. And if I go, let's say, if I increase the value of this, you can see that, have a mirror ball instead of a smooth sphere. So just another example of decimation. Another example, I'm going to hide this. I'm going to let's come here to the direction arrow that I've shown before. And let's see if I come here to this view and I make it visible. Now I have this, I have a rotation in this arrow. Apparently not. Let me set up here a rotation real quick. So 360. So the arrow performs this rotation. Oh, I forgot. I have to turn off the target. So it performs this rotation from 0 to 360. Right. Let's say that I want this rotation, instead of being smooth, I want it to be decimated. I want it to have steps, blocks of rotation. So I come here to the Nodal Motion, and here before I've shown these the multiples, doing multiples with a defined step size. But here the integers, I've added them myself. I did not decimate some data that came in and basically make it change its resolution. I just basically punched in some integers integer value. What I'm going to do now is I'm going to use the object own rotation. So that's why I have this item info with self selected, and I have the rotation coming here, and I'm reading the heading rotation. And I'm going to do the same thing that I've done before. So divide, floor, multiply. So this will allow me to change the resolution of the rotation. And in this case, I can choose the step size to be like, say, 30 degrees. So when I put this on rotation, now the object is going to rotate like before, but in steps of 30 degrees. So it's the same animation. It's the same animation that I could have done something more complex here, but it's basically going to decimate this animation curve. Of course, I can't change. Let me change this, for example, to 15 or to 90 degrees. And so I can choose whatever is the step size. So the last example I want to talk about is probably a bit confusing for this stage, but I think it's neat. It's to transform objects, transform points in groups. So I'm going to choose this array object here. I'm going to reveal it. And if I come to the displacement node editor of it, you'll see that I have this transform 3D compound, which is basically like the transform 1D, but for vectors. So it has rotation in here. And of course, if I rotate these points, if I rotate the object spot, you'll see that all the vertices will rotate around the same center. So this is not very interesting. Let's say that I want to rotate the objects to rotate about themselves. Well, usually for that, people use the part move node, and the part move by Denis Pontonnier gives me the center of the polygon islands. So for example, if I put the object position of the polygon islands in here in the center, when I rotate this, now the torus, the cube, and the gear, they rotate about themselves. So they do not rotate everything as a block. So each of these polygon islands have their own center. Now let's say that I don't want, I want each of these three meshes to rotate about one center. So let's see how can I do that. And that's why I have this setup in here. So I'm just going to briefly explain what it does. So I have these groups filling a space of 1 unit. So I have a torus, a cube, and a gear going from 0 to 1. So this makes one group of one triplet, another triplet, and another triplet. And so I want to define a center for these points. Now, if I just floor it, well, what's going to happen is that I don't want the center to be on the integers amounts. I want the center to be here in the middle. So what I'm going to do, since the step size here is 1, I'm going to divide 1 by 2, and I'm going to add it to the integer. So instead of having 0, 1, 2, 3, I'm going to have 0.5, 1.5, 2.5, etc. And this will give me the center that I want to rotate each of these groups about themselves. So here again, same thing, conjugation of floor, divide, floor, multiply. And then I'm going to add that half of the step. And so that's why I have here the step divided by 2 and added to this bit. So when I put this in the center, let's say that I have 1 in here, so I'm going to have each group, a single triplet rotate about itself. So now the gear, the torus, and the cube, each of those share the same center. But if I put, let's say, 2 in here, now I have 2 of them doing that. Or if I put, let's say, 3, now I have 3 of them doing that as a group. And I can, of course, come here and scale them also as a group, as you can see here. And I can still change this, let's say, to 4. So now I have 4 of them rotating as a group. And well, let's not forget that this part where I divide and floor gives me the integer of the groups. So for example, this is group 0, group 1, and this is going to be group with the index 2. So I can, for example, let's say I can put here logic, let's say logic V, and I can check if let's say I'm going to check if the group index is equal to 0. And if it is, I'm going to make it go up in the y-axis by 1 unit. So let's see, 1 unit. So if I put this here on translate, you see that now this group goes up by 1 unit. So in this case, equal to 0, equal to 1. So I can choose, if I put here another, let me put an integer, int, just for quick interaction. So if I put this here, you can see that I can quickly make decisions for each group. And of course, when I change this here, the group size, the group numbers are going to change. So now this is going to be group 2. and I have them coming up one at a time. So this concludes this video about integers, about how to use indices to set rules or to retrieve data, and also how to transform continuous values into discrete values.